Okay, any questions to start with?
So the diagrams, so I get hybridization, like I know that I know this would be pre-hybridized.
Okay.
But I don't understand energy diagrams, like how that, I don't.
Energy diagrams.
I don't know if that's like something we really need to know.
So if it was the,
It was only one.
like chapters, like questions 22, 23, in that range?
Yeah.
Okay. Okay. I had a couple of questions on Piazza, like, why do we hybridize? What's the driving force? What is hybridization? What's Vesper theory? So I can start with that. Any other issues?
Stuff like orbital overlap.
Okay, that would be in the hybridization as well.
There were also a couple ones where you had to count like how many carbon and hydrogen there were. If we could just go over that.
Counting carbons and hydrogens. Where was that later?
That's the line drawing.
Oh, the line drawing? Okay. Okay, then let me start with this. So we'll start with the line drawing stuff because that's pretty straight, or well, there's a system to that that's a little bit, once you see the system, it might help it. So just with line drawing the structures. So there's different levels of shorthand notation for drawing organic molecules. The absolute longest way to draw a molecule is to draw out each carbon and hydrogen bond explicitly. So like if I wanted to draw that 3-carbon chain, I could draw it out that way, and that's going to take me a little bit of time. So I can shorten this by saying I'll take each one of these groups and I will shorten them down by saying this is a CH3, this is a CH2, and this is a CH3, and so they're all attached together. So you never have a hydrogen with more than one bond. So hydrogens always go on the outside, the carbons and other elements are on the inside. So if I gave you CH3, CH2, CH3, you would have 3 carbons attached and then hydrogens that go around them. I can shorten that even more by doing this. Well, let me do it by doing that. Okay. Now this is called a line bond structure. Every end of the line and every intersection of the line is a carbon atom. So when you see a structure that looks like this, it's carbon, carbon, carbon. I always have to show any elements other than carbon. So oxygens, nitrogens, etc. If there's only carbons in it, then I add enough carbons to give 4 and only 4 bonds. So with this carbon, it has 1 bond. That means it needs 3 hydrogens. This carbon right here has 2 bonds. It needs 2 hydrogens to get to 4. This carbon right here needs 3 more hydrogens to get to 4 bonds. So everything is always enough hydrogens to get you to 4. Okay. And this is just a really shorthand notation because if I wanted to write, for instance, like a benzene ring, which we'll get to, I can write it like that. What does that mean? It means carbon, 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 carbon. Each carbon has 1, 2, 3 bonds, so it needs a 4th, and a 4th, and a 4th, and a 4th. Like that. So that's what the shorthand line bond structures are. I use a combination of maybe both. So I might write a benzene ring. Well, I might write a chain like this, and then off of here write a CH2, CH3 group. And sometimes that's to emphasize that group. So we'll use a combination of the two. And so going back and forth to those, it'll become a little bit clearer and easier as you do more of these structures. And in lab, of course, when I drew the structures out for the lab, I used these line bond structures as opposed to writing everything out explicitly. Okay. So that's the key to line bond structures. The key is every carbon gets 4, not 3, not 5, just 4. Okay. If it had 3 bonds, it would have to have a plus charge, and carbon can't have 5 bonds. It's mistake number 2 in organic chemistry. Number 1, taking it. Number 2, 5 bonds to a carbon. Number 3, primary carbocations, which we'll get to later on. And then I never make it past 3. So there's not a t-shirt out there because we'd have to get to 10 for that. Okay, does that help with the line bond structures? So that's how we convert back and forth. Okay. All right. Is everybody okay with Vesper theory? I want to create a table with Vesper theory because we're going to take Vesper theory and we're going to link it with hybridization. You really can't talk about one without the other. So let me start with this table. Let's create a table that says the number of single bonds plus the number of lone pairs. And so that's going to be one column. Then we're going to have our VSEPR geometry. And then eventually, well, we'll have angles. And then we can add in hybridization. So if I have this chart, I'm going to have 2 single bonds or lone pairs, a 3, a 4, a 5, and a 6 is as high as I'm going to go. And I focus more on electron pair geometries than on molecular geometries. And I'll explain the 2 of those so that we're all clear. You know, these 2 topics of hybridization and like Vesper theory were how many weeks in General Chem? Probably more than 1. And if it's been a while for General Chem, or if you didn't go into that much depth, I want to bring all of us on the same page. So that's why it's good to spend, if nothing else, a little bit of review time on this. Plus, looking at it from how we have to use it in organic. So, the VSEPR geometry then is going to be the way that the clouds of electron density are oriented around a central atom. So our clouds come from single bonds and lone pairs. So those are big balloons of negative charge. They are going to try and get as far away from each other in space as they can. So when you have 2 of those, you'll have 2 clouds at 180 degrees. Right? That'll be 180 degrees. If you have 3, it'll look like that. Now, this is going to be linear. This is going to be trigonal planar. So when you have 3, you have trigonal planar, all 3 of the clouds in the same plane at a 120 degree angle away from each other. Again, this is just a spatial issue. How do I get these lobes as far away as possible from each other because they're all negative and they're all repelling each other? Okay. When we go to 4, what do we have? We've got the tetrahedral. So that's tetrahedral. And that angle is going to be 109.5. That's really the special angle for a tetrahedron. And then when we go to 5, we have kind of combination of linear and trigonal planar. So we have two atoms that go this, we have two lobes that go that way, and then the trigonal planar ones like that. So there's angles of 120 degrees. There's also angles of 90 in there. And then finally, if there's 6, you're going to have like an X, Y, Z coordinate system where we've got all 90-degree angles, and that's called octahedral. And this one is called trigonal bipyramidal. So we've got trigonal bipyramidal, octahedral, tetrahedral, trigonal planar, and linear, going from 2 to 6. Okay. These are what I call the electron pair geometries. So up here I would call this electron pair, our electron pair geometries. Those are the ones I want you to know simply because there's a direct correlation between these electron pair geometries and those clouds and the hybridization. Now you might say, what about bent? Bent is a molecular geometry. So I'll show you a water molecule here in a moment. The water molecule would be bent in terms of its molecular geometry, but I will call it tetrahedral according to its electron pair geometry. So that's something that I do because I'm more focused on the electron pair geometry than I am on the molecular geometry. So you won't have to worry about bent. Now, for me, you won't have to worry about bent or T-shaped or seesaw or any of those other strange terms. The book, on the other hand, may ask you a couple questions on those. But then they'll have a chart that kind of lists what those are. But I'm more interested in these clouds because these clouds are going to be hybrid orbitals that are going to tell us about the hybridization of that atom. Okay. So far so good? Technically I shouldn't ask, is everybody okay? Because I then should ask you another question to sort of verify that that's the case. But we'll get to that, not necessarily right this moment. But if something doesn't make sense, you got to yell. Okay. So I take my water molecule, and it does have a bent molecular geometry because if I erase my lone pairs, all I'm going to see is the bonds. And in a molecular geometry, that's all you see are the bonds. You can't see the lone pairs. But I'm more interested in where the lone pairs go as well. So in this case, I'm going to call this tetrahedral. And if I was the oxygen, I would then have a tetrahedral geometry with the hydrogens forming 2 bonds and the lone pairs in the other 2 orbitals. Sorry, in the other 2 lobes. We haven't moved to orbitals yet, but in the other 2 lobes. So I'm interested in where the lone pairs go as well. So I'm going to call oxygen tetrahedral. And the reason I'm going to call oxygen tetrahedral is because I want to know what hybridization that oxygen is. Okay. So we'll start with something straightforward like carbon, for instance, to look at our hybridization. Okay. So one of the questions that was asked to me was like, well, why do we hybridize at all? And so let me start with the story of why that happens. And it's usually the way I start this. It may have been on the video, but I'll go back through it in an abbreviated manner. So here's what happened with methane. So methane is CH4, that's the molecule methane. Methane is a gas. It is the major component of natural gas. It comes out of both ends of the cow. It is a very potent greenhouse gas. So this is why in the debates the other night they were arguing about eating cheeseburgers. Because if you're eating cheeseburgers, you're destroying the environment because the cows are destroying the environment. Although eating the cows would, anyway, I don't quite. So methane is methane. And what was known was that methane was CH4. So the question comes up, well, what's the structure of methane? And there's different layers of structures here, even that you went through in general chemistry. So the first thing you would say is, okay, I'm going to write the electronic configuration for a ground state carbon atom. And so you would go across the periodic table, 1s1, 1s2, 2s1, 2s2, 2p1, 2p2. And that's how the 6 electrons in the ground state would go into the electronic configuration for carbon. Okay? But here's my problem with that. And the problem is, number one, I can only bond with the uppermost, what's called principal quantum number, which is the 2 or the shell number. The rules are I can only use those as the valence electrons to bond things. So I have 4 electrons to bond things, but in this configuration, my Lewis dot structure for carbon would look like this. I would have 2 unpaired and a pair. Right? And we know that's not what we write in general chemistry. In general chemistry, what do we write? 4 unpaired electrons. We're writing this. So when you only have 2 unpaired electrons, that means, number one, that you can only add 2 hydrogens to it because each hydrogen has an electron to share with the carbon. And so methane would be CH2. If we discovered the octet rule, carbon would not have an octet because it only has 4. It only is sharing 2, 4, 6 and not 8. So we know it's CH4, but yet our ground state electronic configuration for carbon doesn't let us form CH4. Okay? And this is just an observation that people made. They didn't sit down and design it this way. They didn't say, well, I want CH4 instead of CH2. They said, I have CH4, how do I explain that? So then they take this electron, they say, but if I apply energy to it, I can promote that electron up there. I can go into an excited state by applying a little bit of energy. Now, if I apply a little bit of energy, I better get it out. Right? Energy is the driving force for chemistry. Right? Energy is why things happen and why things don't happen. Right? In politics, it's money and power. But in chemistry, it's just pure energy. So if I'm going to invest energy, I better come close to getting it back out. Can I afford a little bit of a loss? Yes, because that's where the energy and the surroundings can come into play. But for the most part, I better pretty much be balanced. So when I put that energy in, what happens? I go to the excited state, and now the excited state has 3 unpaired electrons in the p orbital and 1 unpaired electron in the s. So number one, did I solve my problem of CH4? Yes, because now I have 4 unpaired electrons that I can bond with 4 hydrogens, so now I can make CH4. Did I break even energy-wise? Yes, because those 2 additional bonds that I'm forming are going to give me back more energy than it cost me to put into the ground state. And the ground state, excited state is like chicken and egg, which comes first. Now, I don't know, it just happens. So we get to the excited state. So now I can form CH4. Okay. So problem number 1 solved. But it creates another problem, which is that in methane, all 4 carbon hydrogen bonds are exactly the same. Same bond length, same amount of energy to dissociate them. And the problem now I have is if I used the orbitals to bond the 3 hydrogens to the p orbital, they would have a different bond, slightly different bond than bonding the 1s orbital to the 2s. Why? Because the 2s has what kind of shape? Well, S stands for spherical. And then the p orbitals have these dumbbell shapes, and there's a px, a py, and a pz. And in three-dimensional space doesn't come with axes. Right? If I write some x, y, and z on the board and then you stand on your head, they're different. So there is no real orientation. We decide on that. So the key is that those orbitals then are basically following the x, the y, and the z axis. P orbitals, the electron spends 50% of its time in one lobe and 50% of its time in the other. And there's a nodal plane in between where the electron's never found. Okay? That's quantum mechanics. Let's not blow our minds yet. Right? How does it get from one to the other without ever stopping? Well, remember, electrons are also waves. They have a particle and a wave property. That's, I think, de Broglie. And so we treat them as waves. Like we know there's nodal points on waves that never move. So same thing happens here. But we have 50% of electron density in the 2 lobes, and the sphere, of course, is the sphere. So if we overlap orbitals, which is exactly how we form bonds, we take those the mathematical equations of those shapes of the orbitals, we combine them together to form a chemical bond. Okay? In this case, we're going to take those 2 shapes and we're going to overlap them together. But it's really math. It's really the sort of the Schrodinger equation. Just the shapes being different means that the bonds, when you overlap a spherical 1s with a p, is going to be different than a 1s and a 1s. Okay. So if this was the way it looked, I'd expect to see 3 bonds the same, 1 bond different. I don't. All 4 of them are the same. So I solved one problem, I got to now solve another problem, which is how do I get 4 identical bonds? Okay. And I still would like to get the strongest bonds I can. So if you think about taking 2 spheres and overlapping them, that's not good, right? Because a sphere has 100% of its electron density in that object. So overlapping 2 spheres isn't the best. Overlapping a sphere with a lobe that only has 50% of the electron density, that's not going to form a very strong bond either, because you only have 50% of the electron density in that lobe. So what happens is that we basically are going to mix, or we are going to hybridize the s with the 3p orbitals. Now, whenever we hybridize, we always hybridize the orbitals, and once we have the hybridized orbitals, we put the electrons into those orbitals. Okay. It's like this electronic configuration. Right? The electronic configuration is the same. It's all, you can start with an empty one, but then what's the difference between each element? How many electrons I'm putting in there. So all hybridized atoms, like all sp3s, are going to look the same. They're going to have 4 hybridized orbitals. How many electrons are in each orbital is going to vary from atom to atom. So when I say I'm mixing the orbital sans electron. I'll put the electrons back in depending on the element. Okay. So when I mix an S with 3 P's, I get 4 sp3 hybrid orbitals. They all have the same energy. Now, where they would be in terms of this energy diagram, in between the S and the P, they certainly wouldn't be above the S and the P. Whether they'd be below the S, I don't know. I don't honestly care. Because I've got 4 hybrid orbitals now. Okay. What do they look like? Well, they look like what would happen if you took 4 orbitals, 4 balloons, and made a geometry out of it. So they would look tetrahedral. So sp3 hybridization means you have an atom, 1, 2, 3, 4. Now, an sp3 hybrid orbital has a big lobe and it has a little lobe. So in other words, I shifted the electronic density to one lobe over the other. This little tiny lobe, we ignore until we want to use it. So there's always these little tiny lobes around, and occasionally, a couple times this semester, I'll go, remember that little tiny lobe that we talked about, but then we've forgotten about? We need it. Okay. And so when we write that, there should probably be little tiny lobes around this X. I won't put them there, but I think there's, in the PowerPoint, there's probably one that shows the little tiny lobes. Now, what did I do? In hybridizing, I made 4 identical orbitals. So now I'm going to get 4 identical bonds. Okay, problem 2 solved. Did I make a stronger bond, though? Yeah, I did, actually. Because by polarizing this bond, by putting more electron density in one lobe than another, when I overlap that, like with the 1s of hydrogen, I'm going to get a stronger bond. Because now I've got more of my electron density in that lobe to then overlap. So I just, I'd say killed 2 birds with 1 stone, but that's probably not a good statement. Should be killing birds with stones. But I accomplished 2 things. I made all the orbitals the same, all the bonds the same, but then I made stronger bonds. So in terms of whatever energy it took, whatever energy it cost me to hybridize, I got it back. Probably with a little bit of interest on it. So going to the excited state gives me 4 bonds. Hybridizing gets me 4 identical bonds. And 4 stronger bonds. So why do we hybridize? Because it gives us stronger bonds and it makes the molecule more stable. Okay. And honestly, why do we hybridize? Because that's what it does. Right? I mean, this is what happens. Okay. So that's how the hybridization, that's the way the orbitals overlap. Okay. All right. Still kind of with me? So if you think about the way that we describe bonding, we start with a carbon, we start with a Lewis dot structure. And then we add our hydrogens by making the Lewis dot structure. That's sort of level 1 bonding. Pair up electrons. To do what? Make octets. If the atom can make an octet. Hydrogen can't make an octet because it's only got 2. Some elements can go beyond 8 and form expanded octets. And we'll explain, if you haven't heard the explanation before, why is it? Well, first of all, what are those elements and why can they do it and carbon can't? Why is it rule number 2 that you never form 5 bonds to a carbon? And that has to do with the fact that carbon has these 1s orbitals, but you cannot make them bond, which is not true. If you make them bond, you win the Nobel Prize. Somebody did. A guy named George Olah, when he was down at Case, when Case was not Case Western Reserve, but like Case. Yes, it was that. Yes. It was a technical. I wouldn't have said the exact name, but it was close. So he was actually a chemistry professor down there. He developed these things called superacids that protonate things, and he was able to protonate a CH4 and make a CH5 and violate all the rules that I tell you, and he won the Nobel Prize for that, and all of the other work that he did with superacids. So there's going to be a reason, and the reason is you can't actually hybridize things with different quantum numbers. So you can't hybridize a 2 and a 1. Now somehow he was able to do that, but that's, we're not into winning Nobel Prizes, we're just into the basics of organic chemistry here. But can it be done? Yes, it actually can be done. And chemists are just arrogant enough that if you tell them they can't do anything, they'll find a way to do it. Now, they're not Rumpelstiltskin. We can't turn straw into gold. We can transmute elements now because that's what radioactivity does. But the old alchemists of the day that would promise the king they could turn all of their, straw into gold or their other elements into gold, yeah, we can't do that. But short of that, if you tell somebody, hey, you can't do that, there's going to be somebody out there that's going to try. Okay. In the case of gold, it would be fortune. Otherwise, it's probably just fame. Or it's probably just your name in an organic textbook for the rest of eternity. Okay. So probably on Monday we'll finish this up and we'll talk about, okay, row 3 and lower is where the expanded octets are. And why is that? There is a 2s and a 2p. If there was a 2d, we could mix all those together. There isn't, except in the strange world of quantum mechanics, there's a 2d somehow, which I haven't quite figured out how that exists. But in the real world, there's a 3s, 3p, and a 3d. And so you have to go to row 3 in order to be able to form an expanded octet, because now I have 3 different orbitals to add together to mix. Okay, right? So that's how we form the hybridization. So we go from Lewis dot structure now to hybridization, so that what we have is we have an sp3s bond. The sp3 from the carbon, the s orbital from hydrogen. And so since these overlap head to head, and a spherical orbital has no choice but to overlap head to head. But the hybrid orbital overlapping with the spherical orbital, when you have head-to-head overlap of the orbitals, that's called a sigma bond. So that's called a sigma bond. So that's where the hybridization comes from. Let's do a double bond real quick, because then we'll go back to the chart and we'll fill in the hybridization. And we'll also fill in the rules of Vesper theory. So it's all interrelated. But in general chemistry, you got to take Vesper theory first, then you take hybridization, and maybe you link them back together, maybe you don't. but we have to link them back together so that we understand how these bond form. So level 1, Lewis dot structure. Level 2, orbital picture. Level 3, molecular orbital picture. We're not going there. Okay? We're not going to sigma and sigma star and pi star bonds. If you want to learn about that, you can go to physical chemistry and you can talk all about that. Okay. Maybe I'll throw in a little bit, some basics here and there, but those energy coordinate diagrams in the textbook, those we're not going to. So as far as energy diagrams go, these are the kind of electronic configurations that we're using, but we're using them for carbon. We can use them for nitrogen, oxygen, and sulfur. All we're doing is then promoting up electrons into empty orbitals. And that gives us more electrons to bond, which will make us more stable molecule overall. So that's where the promotion comes from. Okay. Let's say I wanted to form a carbon-carbon double bond. So I would have my 2 carbons with 4 valence electrons with 4 dots. I'm going to bond each carbon with 2 hydrogens. If we're doing Lewis dot structures, we now form the carbon-hydrogen bonds. We pair those 2 together to form the carbon-carbon bond. What do I have left over? 2 unpaired, which I'm going to share, so the carbon gets to its octet. And so now I have a simple molecule called ethylene, which is C2H4. There's my Lewis dot structure picture of the bonding. How about the orbital picture of the bonding? Well, in the orbital picture of the bonding, I basically have now formed 1, 2, 3 sigma bonds. Where do sigma bonds come from? They come from the head-to-head overlap of orbitals. What kind of orbitals? Well, the s orbital for hydrogen, what kind for carbon? The sp3, the hybrid orbitals. You form sigma bonds, you form single bonds from the hybrid orbitals. That's how you form sigma bonds. So if I want to work this process backwards and I want to say, what's the hybridization of that carbon? I need some rules. And the rules are, and we'll go back to the table here and put the rule in. The rule is where I have the number of single bonds and lone pairs. Guess what that equals? That equals the number of hybrid orbitals. So the rules are that single bonds have to come from hybrid orbitals and lone pairs can only go into hybrid orbitals. So what does that mean in terms of the hybridization? If you have 2 lone pairs of single bonds, that means you have 2 hybrid orbitals, which means your hybridization is sp. Then sp2, because I got 3 orbitals, s and 2 p's. Then for 4, it's sp3. And then for 5, it's dsp3 or sp3d, and then d2 sp3. Where the d's come into play, like I said, I don't think we'll make it there today. At least I didn't make it there this morning, but I came pretty close, so we'll finish it up on Monday. Because we'll talk about how you get to the expanded octets. But the number of hybrid orbitals equals the number of single bonds plus lone pairs. So we can work this whole process backwards. I can look at the carbon in the double bond and say, what's its hybridization? And you would say sp2. And the other one is sp2 as well. So now I need to sketch out what an sp2 hybrid orbital looks like. Well, any atom that's sp2 hybridized looks like this. I have 3 hybrid orbitals. The Vesper theory, and this is my shading. That's how I shade the hybrid orbitals. That's with those squiggly lines. Vesper theory would say if you have 3 clouds of electron density, what geometry do you need? Trigonal planar. Now, I just hybridized an S and 2 P's. What do I have left over? A P that was unhybridized. Where does it go? It goes there. So this is the unhybridized. And these are sp2 orbitals. For any atom.
So the reason why it's sp2 is you're only counting sigma bonds, you're not counting the atom.
Exactly.
Okay.
So sp2 because there's 3 sigma bonds in each. Single equals sigma. So any atom looks that way. What's different from atom to atom is how many electrons do I have to put in those orbitals? Again, I need rules. My rules are going to be that p orbitals get 1. They do not get 2, they get 1. And hybrid orbitals can either have 1 or 2, depending on the element. So now, and the corollary, well, the restatement of that is lone pairs only go in hybrid orbitals. I look at carbon, how many electrons do I have to place around here? 4. So 1 in this entire lobe, 1 in this entire lobe, 1 in this entire lobe, and then the 1 in the p orbital spend 50% of its time on top and 50 on the bottom. Any atom will have those orbitals, but putting the electrons into the orbitals, that's going to be for each atom. That's going to be unique for each atom. Okay. So if I wanted to draw this ethylene molecule, what I would say is this. Here's my carbon. Here's my 3 hybrid orbitals. Here's my carbon on this side. Here's my 3 hybrid orbitals. I'm going to point the 2 hybrid orbitals together because that's what I'm going to overlap to form the sigma bond. Then I'm going to have my 2 p orbitals. So I'm going to shade those. I'm going to have 1 electron here, 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 and here, and then 1 in each of the p orbitals. On the left and the right side of the molecule, what do I have? I have my hydrogen 1s overlapping with the sp2 hybrid orbital. What do I do with these 2 orbitals? Right here, I make a sigma bond. And I made the sigma bonds to the carbon and hydrogen. So I think the book likes to give you a structure and say, maybe even a structure like this, and it might say, how many sigma bonds does it have? And you would go 1, 2, 3, 4, 5. It has 5 sigma bonds. How many pi bonds does it have? 1. So a double bond is 1 sigma 1 pi. A triple bond is 1 sigma 2 pi's. Okay. Now, from the orbital picture, what am I missing? Each carbon has 1 unpaired electron, so what do I need to do? I need to overlap the p orbitals. P orbitals only overlap sideways, top and bottom. So they overlap sideways, and that is called a pi bond. So again, in terms of complexity, Lewis dot structure, simple, orbital picture, a little bit more descriptive. in terms of how I'm forming the bonds. So that's how we handle multiple bonds. A couple things. Okay, still with me? In general chemistry, when you talk about Vesper theory, and we're making this table, what do I count up? The number of single bonds and the number of lone pairs. And a lot of times the book or the professor will explicitly say, if you have a double bond, you just treat that as a one bond. So we ignore the pi bond. Why do we ignore the pi bond? Because it's not an essential element of the structure. It's like sideways. It's on top and bottom. It's not adding anything to the geometry. As a matter of fact, could I take this pi bond and could I break it? Sure. I could break the pi bond and what would happen? The molecule would still stay together. Now, it might rotate around, which it can't do once the pi bond is in place. It's stuck. But it could rotate around, or the atom's going to fly apart. Not until I break the sigma bond. Why is a double bond stronger than a single bond? Why is a double bond stronger than a single bond? Because in a double bond, I got to break two things. Why is a triple bond even stronger? Because I got to break three things. So when we talk about Vesper theory and they say treat double and triple bonds as if they were a single bond, this is why. Because the pi bond doesn't add anything to the structure, to the geometry. The pi bond doesn't add anything. It's the single bonds that dictate geometry, which is why we can go back to our chart and say it's the number of single bonds, it's the number of lone pairs, but really that means it's the number of hybrid orbitals that give you the geometry. Okay. So that's why we learn those rules in general chemistry about treating or ignoring multiple bonds, because they just don't make up the structure. What makes up the structure is the hybrid orbitals. And what can go into hybrid orbitals? They're either bonding or they're lone pairs. Okay. All right. Kind of makes sense? We all on the same page? Hopefully if you're bored to tears, that'll end soon enough. So the only issue then is what happens if it's not carbon? So for instance, if I had a water molecule, and notice that that the first step that I'm kind of leaving out here, and I'm assuming, which is probably a good idea, but I'm assuming that we can put together a good Lewis dot structure, which is actually Monday. Monday's topics will be drawing Lewis dot structure, but what happens if a molecule has multiple Lewis dot structures that are legit? Then we have resonance structures. And then when you have resonance structures, they all don't have the same energy, so how do we tell which one's more or less stable? And then of course resonance structures are like your, there's a Super Bowl commercial years ago, and they stole this idea from me. Because I talked about if you bred a pit bull and a chihuahua together, you don't have a dog that's constantly switching back and forth between a pit bull and a chihuahua. They took a chihuahua body and put a pit bull head on it and called it, they put a Doberman head on it. So it was a Dobrahaha or something like that. Anyway, it was like this hybrid dog, right? That doesn't really exist. And orbitals, and molecules don't exist that way. They're the resonance hybrid. They're the mixture. So we have to talk about, well, how do you get the mixture? But then the mixture looks more like one than the other because one's more stable than the other. So that's what we'll talk about on Monday. We'll refresh that. But if we come back here, What's the hybridization of that oxygen? sp3. So what's its geometry? Tetrahedral. So if I want to start sketching out molecules that don't just have carbon and hydrogen in them, I need to make that first step. Look at the atom. Can I tell what hybridization it has? Can I then tell what its geometry is? Okay. And so we'll kind of finish this up with other atoms, go into expanded octets briefly, and then we'll talk about resonance structures. Okay. If you have questions, so the reading assignment will be what's in the reading assignment for Monday. I will put Wednesdays online over the weekend, so I'm constantly trying to move ahead, but stay the same. It gets confusing. For me, just as probably it is for you, like this is for next time, this is for today. If you have any questions, send them to me, put them up on Piazza. Everybody, hopefully, if you haven't signed up for that, you can go ahead. You can see the questions. If you have that question, endorse it. Sometimes if somebody answers a question, which one person did, then if they have the right answer, I'll go ahead and endorse it and say that's a good answer. If I want to add to it, I'll add to it as well. Okay. So feel free to use that as much as possible. The company was like, you have 67 students, or you have, I think at the time, 57 students. You have 57 students signed up for this, but yet there's only like 6 posts. You need to encourage them to use it more. Okay, encouraged. Right? But anyway, you have questions, you can bring them to class. We'll talk about resonance structures and we'll finish this up. Something didn't make sense today, ask as well.